Okay, so let's go ahead and talk about day 3 with our notes. So there are two major types of discontinuities in functions. And before we go any further, I want to make sure that you understand that discontinuities are just breaks in a graph. So there are two types. The first type would be removable, and the second type would then be non-removable. So with removable, we've got a point discontinuity. And simply what that means is, let me take this, it just says that two pieces that connect at an open circle because they approach the same y value. So this is kind of like what you're used to with a hole, okay? And let's take a look at what the graph is going to look like. It says the graph below has a removable point discontinuity at x is equal to 1. So if we take a look at that, we can see that the x value is 1. And so the domain is going to be all real numbers except 1. And the range actually is all real numbers except 1 because it's at the y value of 1. All right, so again, removable discontinuity indicates that there is a hole. Now, let's take a look at non-removable. So there's two classifications of non-removable. We've got infinite, and then we've got jump. Now, jump only is in like a piecewise defined function. So let's take a look at what infinite discontinuity is. It says two pieces that do not connect because they approach positive, negative infinity. So that language is incorrect. It needs to be they. All right. And it's the x and the y values here. So let's take a look at this graph right here. It says the graph below has a non-removable infinite discontinuity at x is equal to 1. So if you notice what that looks like, that is going to be representative of a vertical asymptote. Okay, so vertical asymptote. Okay, that is what a non-removable infinite discontinuity is. This is x equals 1, and that's that vertical asymptote. So let's take a look at jump. So jump discontinuity is when two pieces that do not connect because they approach different y values. So let's take a look at what's happening here. So this graph below, right, has a non-removable jump discontinuity, and it makes sense because it's kind of like there's a jump in those y values, right? So the x is at 1, the y is 1 here, and then the y is 4 here. So that makes sense. It looks like there's a jump. All right, so let's take a look at the domain. Now, you may think, well, wait a minute, there's a break in the graph, so there should be a break in the domain. But I want you to think about with the domain, you know that you have negative infinity all the way to 1, right? But then you have x equals 1, and it goes to infinity. Well, think about what this statement is saying on a number line. So here's 1, you've got an open circle going this way, and then you've got a closed circle at the same point going this way. So when you look at it as a whole, every number is included, including the 1. So the 1 is included because of this section. So I don't care about what section of the graph the x values are on. I care about what are the entire x values across the entire function. And so that's why the domain is going to be all real numbers. And the same thing holds true to the range. If I were to look, I'm going to go from negative infinity. See that this doesn't include the 1, but it does include the 1 here. And this one just goes up to 5, but the fact that this goes on forever says that the range is going to be all real numbers. All right, so if you're confused on that, we can practice a little bit more. Just let me know that you might be a little bit confused on that. All right, so let's take a look at these graphs right here. What I did on each of these was I identified the horizontal asymptote, I identified the vertical asymptote, and then I uh, outlined the x value at the hole. And so that's what I did on all four of these. So let's take a look at what this is saying now. So what we're going to do is kind of compare these graphs and be able to answer the questions here. So let's take a look at f of x. So we are specifically working on, let me make sure that's big here, f of x graph. So let's take a look at that. So over here on the left, we have the graph of f of x, but now let's take a look at each of these components. It says to factor, and this is completely factored form. It is not reduced factored form. And so we should be able to completely factor that, identify the restricted values. You can see that x is not equal to 3 or negative 2. And then rewrite the function in simplified form. And so simplified form means that we are getting rid of these common factors. And then identify and classify the discontinuities from the graph of the function. So we're supposed to come back over here to the left and look at the graph and look at the discontinuities. So we can see right here at x equals -2 that that is going to be infinite discontinuity because that's that vertical asymptote. But then you also have a discontinuity at x equals 3 because that is a hole. So we wanted to classify, which just means to say whether it's non-removable, jump, or point discontinuity. So we've got non-removable infinite at x equals -2. And then we got removable point at x equals 3. And that says what factor cancels out of the function and what type of discontinuity occurs at that restricted value. So x minus 3 is that removable point, and it happens at x equals 3. And it says what factor does not cancel out. And so we can look at it says what does not cancel out of the denominator and what type of discontinuity occurs. So this is the factor of the denominator, and it is non-removable, which means it's that vertical asymptote, and it is the non-removable infinite discontinuity at x equals -2. So I would like you to be able to answer the questions for g of x, and then now I'm going to talk you through those. Okay, so completely factored form. And then the restricted values of the domain, remember we are supposed to set each denominator equal to 0 and solve. So those are the restricted values. This is going to be the simplified form because we've got x plus 3 that we are canceling out. So now we are going to make sure that we are identifying and classifying those types. So again, which factor cancels out? Well, x plus 3 cancels out. And then what type of discontinuity is that? That's point discontinuity. What factor does not cancel out? Well, x minus 1 does not cancel out. And that's non-removable infinite. Okay. All right, so now let's take a look at h of x. So completely factored form. So let's go through, answer the questions, and then let's check our work. Okay, here's completely factored. The restricted values. The function in simplified form because you can see that these guys cancel out. Okay, so we are going to identify the discontinuities that we have. The factor that cancels out is x plus 2. which means it's a removable point. What doesn't cancel out is x plus 3, which means it's non-removable infinite. Okay, so let's take a look at P of x. So go ahead and answer those questions. Okay, completely factored form, restricted values, the simplified form because I am canceling out x plus 2. So not only do we have non-removable infinite, but we have that removable point. What factor cancels out? Well, that's going to be the x plus 2. What does not cancel out? And that's going to be the x plus 3. All right, so this is where we are taking that information. It says, based on the information gathered in the table on the previous page, what inferences can you make? Connecting the equation, okay, so I want you to connect the equation to the location of the discontinuities on the graph. So pause and try and see what you guys think about what connections can you make between the equations and the types and locations of discontinuity. Okay, so let's take a look. All right, so we have discontinuities occur at the restricted values of a rational function. All right, so that's very, very important. So they occur at the restricted values. So now we're getting into the different types. So removable, which is the point, removable point, which is the whole, occurs at the restricted values whose factors cancel out. Non-removable infinite discontinuities, which are vertical asymptotes, occur at restricted values whose factors do not cancel out of the denominator. Okay. So let's take a look at function f of x right here. And I put in the factored form of that. It says rewrite the function in simplified form. So when I say simplified form, that's when you're going to go ahead and cross out those common factors. So that's what we end up getting. It says at what x value does the graph of f of x have a point discontinuity? So where was that x at that point discontinuity? So we said x, that it has a point discontinuity at x is equal to 3. Okay, that's where the point is. And then on our function, we know that that's an undefined value. So we know that x can't equal 3, which is why it appears to be an open circle. Okay. Find the value of the simplified form when the function, of the function when x is the value of the point discontinuity. So what happens is now we're trying to figure out, excuse me, now we are trying to figure out the coordinates of the whole. So we have to make sure that we are plugging in the x is equal to 3 into the simplified form. So there's the math, and I get when x is 3, my y value is 7/5. And so now we are able to determine the coordinates of the whole. So I would like you to be able to answer those questions for g of x. Okay, so hopefully you were able to come up with our simplified form. The x value of the point discontinuity is going to be at -3 because that's where those common ones are. So I'm going to put x is equal to -3. That's where the x value of the whole is. And so now we are going to evaluate that. And then now we can determine where the location of the whole is. Whoops. All right. So now let's try h of x. So go ahead and answer the questions that follow for h of x. Okay, so simplified form. The x value of the discontinuity is going to be at x is equal to 2. Oops, get rid of that right here for you. All right, and then here when we evaluate, we need to be able to plug in -2, and the location of the hole is -2, 1. Okay, so let's go ahead and do p of x. Okay, so let's see how well you did. Okay, so we've got the factors simplified. We should see that the x of the whole, these are the common factors right here. So we should have x equals -2. We know that it can't equal -2 because that's a discontinuity, but the x value at the whole is -2. So what we do now is, again, just plug it in, evaluate to find the location of the hole. All right, so based on the information in the table above, what inferences can you make about how to find the coordinates of the hole in the graph of a rational function? Okay, so first, what we did, let me put this here. Okay, so first we need to simplify the function, then evaluate the function at the x value of the point discontinuity. So that is important to make sure that you understand how to be able to find um, the coordinates of the hole. Okay, and I believe that is it.